here's a quick interlude on scales of movement. I may iterate with all possible emphasis that the source of my technical equipment is scales, scales, scales. That's a quote by a virtuoso pianist. I really should have said it with a strong German accent. And so I'm going to talk about what does it mean to talk about scales of movement and why they're important. And this is best shown with an illustration. We have a track. This is just a sort of correlated random walk. Its angles are, clustered around 0. Its steps are all 1. And as we subsample this thing, we see how those angles become less and less clustered, and the step lengths change, the distribution gets wide. And the question is, at what point, at what subsampling, do we emulate something that's kind of a random walk? Have we lost the information at autocorrelation? And so the characteristic time is the point, the tau, at which we lose all correlation. And so there's a mean movement, potentially. That particular plot didn't have a mean movement, but that's sort of this length, this effective length scale is how much you, on average, move in a direction given a certain time. And this length scale of randomness, sigma, is sort of captures how much movement is random on top of your effective movement. If you take away the effective part, what's left over? What's the length scale of that? And so these two parameters, mu sigma and tau, define what I call an MST walk. And it is a random walk with advection that is parametrized in terms of those scales of movement. And I kind of make an assertion that those scales of movement are very important for a lot of processes that I'm going to talk about shortly. But first, how do we find them? Well, we can find them sort of in an empirical way. We can sort of get these clustering coefficients. This is that walk. And we see what's the clustering coefficient at different subsamplings. These are taus. We get this sort of randomized envelope where we see what happens to estimates of that clustering coefficient for a truly unclustered walk. And we see where our data sort of collides. I don't know if you can see the green line, but where it hits there. So we have some time scale around 20. We look at what happens to that estimated step length, mean step length, and we sort of return this sigma that is about 13.5. That's a very empirical approach to getting a scale of movement. There's some purely theoretical ways. That time scale is related to 1 over our autocorrelations from that first analysis. It's also related to 1 over the real part of alpha from the complex movement. And then there's some sort of, I guess we call them semi-empirical ways, and that is to look at, again, this is the same sort of plot, we're looking at the clustering coefficients for different values of certain initial clustering, ranging from 0.84 to 0.96, and we see how they drop off, and we can fit sort of a curve very well to that drop-off, and we can basically redefine clustering in terms of a half-time, the time that it takes for that clustering to drop to 0.5. And that's sort of an intrinsic time scale of randomness. And I'm just going to briefly run through an application of that to some dugong data that I had the pleasure of playing with. This is a dugong. It's a tropical Sirenian, highly endangered, but fairly abundant in this bay in Australia, where they tag them. And in contrast to us slipping around on these cold rocks in the North Pacific, these people, dive into these tropical waters and tether a little floating bob with a GPS thing. So they get really excellent data because it's always on the surface. The dugong doesn't go very deep, and it's kind of always exposed. So that's my friend Dave leaving this data. And there's a lot of that I have done in the past with this dugong data, but here I'm just going to show how, here's the track of a dugong. It's very gappily sampled. So if we look at, you can get sort of a net clustering, but what does this really mean? If some of the intervals, most of the intervals are around 15 minutes with a lot of spread, and some of them are up to several hours. So we can apply that thing, we can sort of get a half-time autocorrelation. So remember how complex the first two results are. The Dugan results are a little bit nicer. Yeah. That's the result. So what that tells you is that if you were unaggregated, and obviously Dugan also has tons of behaviors going on there, but aggregated, if you sampled that Dugan every 9.55 minutes exactly, and you estimated that clustering coefficient, you'd get 0.5 would be its clustering. So this is kind of an order of magnitude for how persistently it moves. So at every about 20, on the orders of tens of minutes, it's changing its behavior in a way that loses the information about it. So this sort of little interlude on scale, the final chord, is that yes, there are at least 3 ways to obtain these scales. Now,